So may I ask for your attention again? Yeah, before the other presentation will start, I have to introduce you our sponsors. We have two sponsors of the summer school finally. The first one is the project Eagle.1. I have already told you about the project. This company provided us the possibility to do the hardware experiments on the island tomorrow. So you will get the possibility to see the place where these drones are tested. Also, this company is hiring. So if you would like to do something with such interesting drone, let's say, you are welcome to join the team. In case you would decide to do that, you will be closely cooperating with our group, so you can decide if you would prefer to go more for the industry or to go to my group for doing research. So this is the first sponsor I wanted to introduce, and the second one is going to be company Algorithma. Hopefully it's pronounced well. It's from Abu Dhabi. They are also hiring. There is a quite nice research team head by my friend Tarek. He was previously in with Khalifa University and working on the Ambitzer competition, but now he went to industry. They are working on aerial robots as well. You could read it in the leaflet we have distributed here. So they are looking for engineers for UAV swarms, UAV autonomy. So of course the advantage of such a company is quite nice salary. So if you will decide to try to get there, we will meet also soon, because we are going to participate in the Ambitzer challenge in beginning of 2020, so we will stay there 1 month for tests in Abu Dhabi, so we can meet then. Okay, so thank you for attention regarding our sponsors, and now we can continue with our program. Another presentation will be given by Jen Chung. Thank you very much for coming, and please tell us something about learning to coordinate. Thank you again.
Thank you, Martin, and thanks for inviting me to present here today. Actually, I got to say, to begin with, it's such a pleasure to come to a venue where not every single talk you hear is about deep learning. This has been a very nice break for me. But having said that, my talk will be a little bit different to a few of the other talks that you've seen earlier, mostly because we're coming at it from a different perspective, more from the multi-agent coordination perspective. So I have to give you all a warning. Again, there will be no drones in this talk, same as Heiko's talk. And actually, towards the end, we might not even have any robots, but we'll see. We'll see how we go. So I want to start off by talking to you about a couple of different mechanisms that we can use for doing learning for coordination. And so for you to really understand what the challenges are, I'm going to talk about it in terms of single agent learning as well as multi-agent. But we have to start off with the single agent stuff. And the two methods that I'll talk about are reinforcement learning and neuroevolution. So just for a show of hands, how many people here are familiar with the concept of reinforcement learning? Oh, fantastic. What about neuroevolution? A little bit fewer. Okay, I apologize. This will be incredibly brief. There will be like 5 slides about each one of these, and they will not be in any way comprehensive of the decades of work that have gone into both of these methods. But hopefully it will give those of you who don't know yet about these two methods some idea of what the challenges are. Okay, so once we have an idea of how we can do multi-agent learning for coordination, I'm going to go and dive into what the 3 kind of big problems are when you're dealing specifically with multi-agent learning. So these things don't exist in single-agent systems, and you'll be able to see immediately why. But there are some ways that people have come up with in terms of how we can deal with these problems. And then finally, we're going to get a little bit philosophical, and we're going to start asking questions like, well, if we take a big step back and really ask ourselves, what is an agent in terms of a multi-agent system, and how does our decision of what an agent looks like, how it's defined, how it interacts with everybody else in the team, how that can have really severe impacts on how well your learning algorithm is going to perform. Okay, so just a little bit of motivation for why you would want to do learning for coordination. So learning falls underneath this idea of implicit coordination. So in the previous talk, Alejandro was talking about communication, which is somewhat more in the explicit coordination part of things. So in explicit coordination, if you have two tasks, for example, and you have two robots, then what usually happens is that they communicate to each other and then they agree, and then everybody's happy. And this is what explicit coordination in a very, very brief setting looks like. For implicit coordination instead, you have the same setup, but instead of communicating to each other, you might have one agent pick an action, and the other agent observes that action, and then from there, makes a decision about what it thinks it should do, given the overall task and given what the other agents have done. And in this case, you don't have any kind of explicit communication happening. There's some observation of what the other agents are doing, but you don't really require that inherent communication. So there are some limiting factors for why you would want to choose one over the other. In explicit coordination, I mean, Alejandro did a really good job explaining all of these challenges already, but again, just to recap, so in some scenarios, really, if you take too long to communicate or take too long to make a decision, you really have these missed opportunities. And in really dynamic environments, this is very common. Sometimes there's security issues. You don't want people intercepting your communication messages. The complexity in the mission and also in the negotiation mechanisms can be quite challenging to do in real time. And sometimes you simply just don't have a communication channel. And so under those circumstances, then you want to consider using something that's more implicit. Now, we're going to focus on learning-based methods for multi-robot coordination. There are other implicit methods like belief-based planning and so on, but I won't touch those, not in this talk. And we're going to focus on learning-based methods. And so these ones are solutions that train control policies via reinforcement learning or evolutionary methods in general. These are the two big ones. And the problem characteristics that we have are that you have relatively large multi-robot systems, so we're talking 10 to 100 or so, situations where you use like more than two, basically. And then your system evaluation signal you can get readily from the environment. So you might not know exactly how well you're doing all along the way, but something from the environment will tell your whole team how well everyone is performing at the end. And these are scenarios that also we allow offline training to be feasible. It's not something that you have to do learning online. So simulations are available and can be used to solve these problems. And so the general paradigm when it comes to these learning-based methods is really to offload all of the hard work of coordination into the training phase. So you're really putting all of your engineering effort into working out what kind of an learning strategy you want to do, rather than trying to engineer the control policies directly. So you engineer the learning strategies so that when you do this whole big learning problem, you try to solve it using reinforcement learning or evolutionary methods, that they will be able to discover the correct control policies at the end of it all. Okay, so to begin with, this is the start of my very brief introduction to reinforcement learning. The overall goal is to work out how an agent needs to interact with its environment to learn some sort of task. And I think in Heiko's talk yesterday, he introduced the multi-arm bandit problem, which is one of the classical problems in reinforcement learning, actually. And so in that sort of domain, your agent is you, the player. Its environment is the set of slot machines that you can learn how to play, and the goal is to get the largest payout. So it's really straightforward. Okay, and so the outcome is some policy that's going to tell you, well, if I'm in this particular state, what action should I take? That's the goal. And so we have some squiggly symbols. You've got your policy, you state your action. These things are going to keep showing up. You look at all of the possible sets of states and all the possible sets of actions. But we don't just want any policy. When we try and solve these problems, we are always looking for the optimal policy. And every time you see this little star down the bottom, it means we're talking about the optimal version, whether that is the optimal policy, which is pi, or the optimal value function, which is q. And so these two things, the policy and the value function, are typically very closely connected. So there are some methods which choose to solve the policy directly and others which choose to solve the value function. And ultimately, if you basically solve this equation at the end to decide what your robot should do, then you're actually solving for the same thing either way. Okay, so the thing that characterizes reinforcement learning problems, or the typical ones that you see here, are in cases where you aren't really able to specify the policy or the value function very easily. So we're talking about like continuous states and actions, things where you know when you've achieved your goal. So it's really obvious, you got a payout, it was a high reward, you know that you're doing very well. But it's really hard to know like what exactly is the sequence of actions that I should take to get to that particular goal. The multi-arm Bandit problem is probably not a good example because it's a one-step process. But say, for example, another classic one, which is the cart pole, where you're trying to balance an inverted pole. And all you can do is apply forces to the cart to allow it to move either left or right to try and balance that pole. It's really hard to actually come up with a state machine that's actually going to tell you how to do that. But when it's balancing, you know it's balancing, right? It's very easy to see that that's happened. So what reinforcement learning does is it provides a really structured framework for performing this kind of trial and error search across the whole domain space with concepts of delayed rewards. So what happens when your reward doesn't come until like 10 or 100 steps later down the line? How do you propagate that information all the way back along the whole set of states and actions that you took to get there? So we have this cart pole problem. Let's take an example. If we wanted to solve this, we want to balance this cart pole. You know, as I described, you can apply forces on the cart. The cart only moves left or right across this space. And the goal is to keep this pole upright. Now, you can basically interact with your environment. You can try random actions. You can apply random sets of forces, and you can see what happens. Like, was it successful? Was it not successful? And then somehow the environment is going to tell you whether or not you were successful. So either you, as the external assessor, says, yes, you're balancing it for 1 second, so you get +1 reward, or something at the end of it is going to be able to measure that for you. And then finally, with that information of how well you did perform, you can update your value function to try and maximize your future expected return. And so by updating your value function, you're updating your policy, and so that changes how you try and explore next time round. And basically, this whole thing repeats over and over until you're satisfied with the policy that you have. Okay, so how does it look in reality? So here's a very simple example. Let me see if I can get my mouse back. So this is not my work, this is work by Martin Reed-Miller. Actually, he's one of the earliest guys that worked on deep learning as well, so just to throw it in case you're all missing it. Okay, so not very exciting in the first round. Remember, at this point, it has no idea how the system behaves. All it knows is that it can either push the cart to the left or to the right. So at the beginning, it's going to look a lot like this for a very long time. There's going to be a lot of random actions, a lot of random exploration, but hopefully at some point, we can get to a stage when actually we are starting to see some progress. So after 180 trials of just randomly pushing it, eventually it gets a signal that's like, hey, actually, if I do this in this sequence, I can actually balance the pole. It's not perfect, so we can continue learning for a little bit longer. And so in the end, you end up with a policy that is, reasonably efficient at getting the pole to invert. Also to mention that it has to balance it in this region here, so it can't balance out here. It actually has to be right here. And these kind of policies are actually reasonably robust because you never told it anything explicitly about how the world's going to behave. All it knows is that if the pole is at this particular angle, I should either nudge it to the left or to the right. And so you have these really pesky kind of engineers coming around and messing up your answer. It's able to recover even though nothing in its learning ever told it about people giving it perturbations. So it's pretty powerful. That's, I guess, the take-home message from here. Okay, so this is the diagram that you're going to see quite often if you work with reinforcement learning. You have an agent, you have the environment that it's going to operate in. The environment will inform the agent of what kind of state it's currently in and also what its reward is. And then the agent, having this information, is going to decide on what particular action it's going to take at the next step. And then having taken that action, the environment is going to progress, it's going to transition to its next state, and then it's also going to emit a new reward to the agent. And so we can write this quite neatly down here in this kind of a relationship. So every state and action pair is going to emit a new state and a new reward. And the goal here is to, again, learn what the policy is in order to maximize this. And so here you actually have a stochastic policy. So your policies don't have to be deterministic. They can have an element of randomness to them. And here this policy happens to be a probability of picking a particular action given a particular state. Okay, so knowing all of this, we want to, in reinforcement learning, basically maximize this total discounted reward. So for every step I get some reward, I want to incorporate some idea of how good it's going to be in the future as well. And how kind of greedy, how myopic we want to be gets captured in this gamma value. So if this gamma is very low, so if we have it as 0, then the only thing that matters to us is the immediate next reward. But if this gamma is high, say close to 1, then we really care about stuff that's going to happen in the future. And that's how you tune it. And regardless of all that, the whole point is that reinforcement learning actually doesn't require a model of the environment. If you don't have a model of it, if you can't simulate it, it's totally fine, so long as you can get this reward coming out of it, and so long as you can measure your state at the end of it all. So if you have some way of accessing all of that, you don't actually need to model your environment. Of course, if you have a model, you can also use it using dynamic programming and other methods like that. Now, the other important thing here is that reinforcement learning relies on this loop being exactly one loop. And what I mean by this is that the system needs to be Markov. And what this means is if we have our Markov decision process, it has this tuple where we have our states and actions, which you've seen before, which are described within there. And then we also need to know what our transition function is going to be, or have someone who tells us how we transition. And this transition function can be stochastic again, like in this case. And we also need to have some way of representing what the expected reward is. And once we have all that, we also have the discount factor if you want to incorporate that in there. And the important thing to note here is that these two variables, this version of the tuple, your transition function and your reward, are only functions of the current state and action. They do not care about what happened in the past. They don't care about how you got to where you are so that you could perform this action. Everything needs to be totally crystallized in the current state and action. And if that is the case, then we describe these kinds of systems as being Markov, where the history doesn't matter. Everything that we need to know to make our next decision is available to us in our current state. Okay, so then if we have all those things, if all those things are satisfied, then we have this theorem which says that for any Markov decision process, there exists a policy such that the expected value of the return for any policy and for all states is going to be achieved by the optimal state action value function. The one that optimizes this is going to be the policy that you're looking for. And so I guess what's important here is that basically there's always going to be a deterministic optimal policy which can be formulated as such. This is basically gives us hope that we can actually solve the problem. Not that it's easy to find the problem, but that the solution actually exists. Okay, so if we have this kind of relationship that the optimal policy is going to be always maximizing, or picking an action that always maximizes the optimal value function, then the Bellman optimality equation is one that actually gives us this recursive relationship when we unwind it all. So we know that the return is basically the reward now plus some gamma times the reward later, and so on and so on. And basically, if you unwind all of that, you can actually write out this equation here. And this gives you a recursive relationship to allow you to do some updating as you get new information. And so Q-learning, which is one method of reinforcement learning and one of the more popular ones these days, basically takes that information and kind of shoves it into the temporal difference here. And so what it allows you to do is to say, well, if I get a piece of information as I'm randomly exploring this state, what I can do with what I know about my optimal value function so far is to basically run it through this equation up here to update what I think is going to be the best values to represent my states and actions. And so it's actually a very simple relationship, and it looks a lot like a P controller if you're looking at it this way. So your new estimate of your value function is the same as your old estimate, plus some step size multiplied by the difference, by the error, between what you thought you were going to get versus what you actually got. Sorry, the other way. What you thought you were going to get versus what the environment actually told you you got. Okay, so ultimately, I mean, I think RL is one of the more easy methods to intuitively understand. Implementing it is very tricky, though. Implementing it properly. And the reason is because there's a whole bunch of caveats, which are very hard to kind of address in real-world problems. So the first one is that it requires your problem representation to be Markov. And for a lot of robotics problems, for a lot of real-world problems, it's kind of hard to get a Markov system. There's always going to be some unknowns that you really just can't model. And you kind of throw it all in there and say, it's part of the stochasticity of the transition function. But if it's really severe, you're going to have trouble learning this sort of stuff. Second thing is the exploration versus exploitation problem, where basically we're doing trial and error search. But at some point, you want to be drilling down into finding out what that actual optimal policy is. You don't want to be doing random stuff all of the time. So given that that's the case, you have to figure out, what's the kind of schedule that I should have for exploring, and then deciding when, okay, I think exploration is done. Let's go and exploit now. And the final thing is that it assumes that repeat observations from any set of states and actions are going to give you exactly, or not exactly the same, but that the rewards that you get are going to be sampled from a stationary distribution. And this is kind of an extension of the Markov assumption up the top, which is basically saying that if you're in one state, you pick an action, the reward that you get is going to be sampled from the same distribution every time. And as you'll see when we come to the multi-agent learning side of things, satisfying all three of these, or at least the first one and the last one, actually become quite tricky. Okay, so that was my very brief introduction to reinforcement learning. Evolutionary algorithms, I'll show you, my description is going to be very brief, even briefer, because I use a very simple version of this. So hopefully I don't insult anybody out there who does evolutionary algorithms, does all the bells and whistles. We use a very simple version. So evolutionary algorithms, the goal is actually just to find an optimal response with respect to some fitness. And so it's not specific to learning control policies or anything like that, but it can be used because you're trying to optimize for something. You're searching for the optimal solution. And so if we're using evolutionary algorithms to learn a control policy, then what we can rewrite this as is our goal is to find the optimal policy with respect to some reward function. And so in neuroevolution, which is the one that I'm going to focus on, as the name suggests, what we're going to be evolving is actually neural networks. We're going to be having a look at how our control policies can be represented as a neural network, and then when we run our evolution, we're basically trying to find the best set of weights that represent our control policy. So if this is a very simple example of a neural network, we have our states as our input nodes, we have our actions as our output nodes, you can have any number of hidden nodes which are going to be connected in some way with some set of weights. And these weights here are just scalar values, so basically going from this first set of nodes to the second set of nodes is a matrix operation. And usually you throw in some nonlinear activation function, because otherwise the whole thing collapses to one linear function. So there's nonlinear activation functions inside each layer, and sometimes you want to add a bias term if you want to allow extra representational capacity. And so how do you use an evolutionary algorithm to learn a control policy? Well, a simple evolutionary loop, a very, very simple evolutionary loop, is you start off by initializing your policy of neural networks. You initialize it the way that anybody else initializes anything, by choosing random numbers. And then the first step you take is to mutate. So you take your policy, you get your set of control policies that you have from before, and you add some amount of noise into your system. So that can involve picking, a subset of the weights to add some, Gaussian noise to, or you can pick any other kind of mechanism to do that. Once you have double your population, you can pick each one. You can assess each one in the simulation, and you can work out what its fitness is. So you try, control policy number 1, you see how well it worked, you can try that all the way through, and each one of those will get a score of its fitness. And then given that score, you can then run competition. So you want to retain your K best, and you can decide how you want to do that. But there's a couple of different things that you want to be careful of when you do that, and we'll get to that in a couple of slides. So once you've retained that, basically you close this loop and you continue doing this. And at some point you say, okay, I think these guys are good enough, let's push it. Let's take our best solution out of here and we actually implement it onto our robots. Okay, I think this neuroevolution is also a very simple concept of how you would do learning. But of course, like anything else, there's a whole bunch of caveats that you have to be careful of. So there are a lot of decisions that you have to make when you set this up. First of all, you have to choose what network structure you want to have. And you're also, in that case, you're basically trading off how expressive you want your system to be. And that's, the more weights you throw in, the more expressive it can be. Versus the complexity of learning all of these weights. So the more weights you have, the harder it is to learn all of them. Inside the mutation, there's a whole bunch of questions that you need to ask yourself. if you're going to just be applying some amount of noise to it, well, how do you choose which weights are going to undergo this mutation? How much noise are you going to add to the system? Are you going to do something fancier, like using crossover? Are you going to mutate the whole network topology? And when you start delving into these kinds of questions, there's actually a lot of choice that goes in there, and all of these choices are going to make some impact on how well your system's going to learn overall. And finally, in the competition, there's also a couple of things that you can do there. You can either use like a binary tournament where you basically split the whole system in half and you compare them in pairs and you keep the best one. Or you can just keep the top half. And the thing that you're balancing with in that case is making sure that you maintain population diversity. And what I mean by that is population diversity is very important for evolutionary algorithms because evolutionary algorithms are powerful in the case where you have a very non-convex solution space. Because you're basically running these whole things in parallel, you're basically trying a whole bunch of different solutions at once, you want to make sure that not all your solutions end up in one kind of local minima. You want to try and make sure that there's some diversity in your system so that, if 50% of your solutions end up stuck in one local minima, there's some chance that throwing noise into it is going to bounce it out of that space. And so that's kind of where evolutionary algorithms are powerful, maybe more powerful than using RL, for example. But then, as always, you have to be careful that you're keeping aware of that. Okay, so that's RL, that's neuroevolution. Now let's actually switch gears and stop talking about single-agent systems and actually look at what happens when we have multi-agent systems. So there's a couple of different ways that you can go about doing learning for coordination. So the first one is joint action learners, and the second one is concurrent learning. These are the two broad mechanisms that you can use. Now, joint action learners are really just taking your whole multi-agent, multi-robot system and then thinking of it as one big agent. You're trying to solve the joint state action policy for all of these robots at once. So there's some benefits to doing that. First of all, the system is Markov because you can observe what's happening everywhere in the team at once. And the reward that's been applied to the whole team is actually going to be, a strong signal for how well the whole team is doing. The problem, though, as many of you probably figured out, is that the dimensionality problem is very difficult. So the more robots, the more agents you want to throw into here, the bigger the problem becomes. And so that, in turn, makes exploration become infeasible. Part of reinforcement learning is that you always have to have a non-zero probability of seeing every possible state in action. And if your state in action space gets exponentially larger, it's going to get very, very hard to see all of these things and to be able to explore this space efficiently. Now, on the other side, concurrent learning basically says, all right, I'm going to let every single one of these robots, every single one of these agents perform its own learning routine. And then what I'm going to do instead is couple them all according to a team reward function. So even though this guy over here is learning how to be a goalkeeper, the whole team is still going to get one reward, which is how many goals did they score, or what was the goal difference between their team and the other team. Okay, so the benefits of doing this is that your problem dimensionality is fixed given the size of the state action dimensionality of each one of these agents. But of course, the problem now is no longer Markov. You have partial observability. So something that an agent over here is doing might influence the score a lot, but this guy has no idea if he can't see it or if he has no access to that information. So this whole system becomes very random to some of these agents in the system. And then you have the issue of non-stationarity and all this sort of stuff that we're going to get into later on. So as you can imagine, we like to make our lives difficult, so we focus on concurrent learning. And so in concurrent learning, just to reiterate what I said before, we have a team of distributed learners. Everybody is doing their own learning algorithm. The agents are coupled by their team performance, so they get one score that is the global evaluation of how well the team performed, and then the goal is to find the optimal set of team policies that are going to maximize this team score. And so everything here is going to be predicated on the joint, which is represented by Z. So that's everybody's state action space all concatenated together. However, when they're learning, they're only learning according to their own state and their own action. So there's going to be this disjunct here that we need to try and bridge to make this problem actually solvable. Okay, so how do we implement this? Well, for reinforcement learning, multi-agent reinforcement learning is quite simple. Each agent basically runs their own RL loop. Nothing really changes there. The only thing that's different is that this reward is now going to be a function of a bunch of variables that they cannot access. And that would be the states and actions of all the other agents in the team. For, let's see, cooperative coevolution, so this was the loop that we had before for single agent evolutionary algorithms. Now, if we want to do it for multiple agents at once, instead of initializing one population, we now need to initialize M populations, where M is the total number of agents in the team. And then when we mutate, we mutate everybody at once. And then the one thing that really changes is when we go to doing the evaluations, when we go to test them all, we actually need to make some decisions about how we pick a team. So the simplest way is really to just pick one randomly from each one of these populations, one control policy, formulate that team, and then evaluate how well that team performs. And basically do that sampling without replacement so that you basically have to run this, K times or 2K times to get everybody's evaluation. And then the competition is exactly the same. You pick your K-best out of all of the available ones, and then you close that loop. Okay, so this is the end of the introduction for reinforcement learning, neuroevolution for single-agent systems and multi-agent systems. And so what I want to dive into next is the three major problems, which is structural credit assignment, agent noise, and tightly coupled tasks. So before I dive into those, are there any questions on RL, neuroevolution, burning questions that you want answered? Yeah.
How you said that the probability of each option is to be non-zero?
So the probability being non-zero. That's
yes. How do you make sure that you have all the probabilities if you're randomly selecting from each?
right. So the probability requirement, the requirement of being able to reach every possible state action space. Actually, in this one, it's a little bit more complicated in here because the state action, or at least inside this loop here, you need to guarantee that all of these things, the way that you mutate them, will allow you to explore the full available space of all the possible control policies. Right? And so for RL, it means that if you're doing a stepwise kind of thing, then you have to make sure that you don't have an absorbing state in your Markov system, where basically once you get there, you're stuck and you can't explore anymore. There always has to be some way of reaching every single possible state in your system. Otherwise, there's a possibility you'll get stuck, you won't see, and then maybe the optimal solution lies in a space which you can't reach. Yeah. Other burning questions? All right, let's go on to the structural credit assignment problem. Okay, so what is it? Let's take a look at an example. So here is a clip from RoboSoccer. And so here, I mean, it's going to be very exciting. I want you to watch what's happening. Oh, he passes it to the center, dribbles it around, passes it out. Oh, he passes it back. He shoots. He scores. Woo, everybody cheers. Okay, that was kind of hard to see. So there's a lot of stuff going on there. Let's slow it down. Okay, agent on the side passes it into the center. Center dribbles it around an opponent, passes it out, immediately gets deflected back because he was trying to psych out the opponent, and then he shoots, he scores, and everybody's happy. So, the whole team gets +1, but who deserves to get the +1? Is it the guy that scores? Is it the guy, the teammate that he passed it to, who then did the assist back to him? Or is it the one right at the beginning who knew how to set up the play? This is what we talk about when we're thinking about structural credit assignment. You get one reward, but you've got all these agents that are acting in this system that are contributing to this reward. How do you actually work out who did what? And not only that, but there's players at the back here, the defenders from the same team. Should they get a reward? I don't know. Maybe, maybe not. We'll see. Okay, so another domain. Let's talk about the multi-rover exploration domain. This is like an informative information gathering problem where you have some set of robots, some set of rovers that you want to send to some remote location to pick up some information, gather some information. So here, these things in the environment are features of interest, points of interest, and we want to collect some information about them. So we could send one robot, but of course this is the multi-robot system summer school, so let's send more to make this job easier for us. And so one robot might decide, he wants to take this trajectory, another one wants to go this way. These three might all decide to go to the same location, and these other ones, I don't know what they're doing. They're just going to wander around. So they all get some set of observations, and this all gets transmitted back to the base station, and at the base station, the external assessor, whoever this oracle is, decides, good job, the team did a good job. Okay, so this is the information from a global team evaluation. But who of all these agents actually did a good job? You know, some of these are obvious, like the ones that actually went to go see a point of interest, like these guys over here and this one over here. But you know, how good a job did these guys do? If they all went to go see the same thing, how useful is that for me? And this is what we're trying to unravel when we talk about the structural credit assignment problem. So this is the possibility where you have lazy teammates, and you want to root out these lazy teammates to make sure that they don't get a reward that they don't deserve. So this team receives one reward, and this is how they're coupled according to their learning algorithm. But you know, we're really trying to work out what did this agent's action actually contribute to that number. So the problem here is that the more agents you have, the worse this signal-to-noise ratio gets. So if you only have 2 agents and one guy's slacking off, it's a little bit more obvious than if you had like 100 agents and one guy slacks off, right? So this has some analogies to the temporal credit assignment problem, which you may have heard of in reinforcement learning, and that's where you know, your reward comes right at the end, and you're trying to work out how to assign that credit back along your trajectory. This is similar, but it's structural in terms of all of the agents that are contributing to this information. So when we talk about this, we're really looking at the reward function. So how can we actually engineer this reward function so that we can unravel the individual contributions of the agents? So typically we have access to the global reward, so we know how well the whole team performed. The problem with this is that it doesn't really capture the individual contributions as we know. The other thing that people can do is you can use the local reward, where really you ignore everybody else in your team, and you're just looking at how well you performed. So you know, this will introduce double counting. So in the case where you had those 3 rovers all going to the same location, they'll all think that they did a fantastic job. But really, they're just wasting time. They could have been spreading out and doing something more useful. And it doesn't, this local reward also doesn't capture individual sacrifice. So in the case of the robot soccer, you know, the guy that deflected and passed it back, you know, that guy could have scored and then got the reward, but by passing it back, then the whole team gets the reward, and it doesn't capture the value of actions such as those. So one method that has been used actually quite popularly in multi-agent learning literature is to use the difference evaluation function, or the difference reward. And this is really trying to capture basically individual contributions. And it's formulated like this. It's quite simple. You take the global team performance, so the number that your external evaluator told you how well the team performed, and basically you're trying to extract how well would the team performed had you done something else. So this is the global system performance, the world with me, and this is the global system performance excluding the effects of agent I. So what would happen in the world without me? And so this is pretty nice. I mean, it's quite simple as a structure. It seems pretty obvious, but it also has a couple of nice properties associated with it. So it has this sensitivity. So it's learnable in terms of this one directly calculates that agent I's contribution, but it's also aligned to the system performance. So we can check that by looking at the partial derivatives. So by taking the partial derivative of this equation up the top with respect to agent I's action, so the left-hand side, we have it as partial derivative of agent I's action, but over here, this second term is not a function of agent I's action, and so the partial derivative goes to 0, and we can see that actually these two are the same. And it's nice, this is particularly nice because it means that if you try to maximize D, then you're maximizing G. And this is very important because you don't want to be maximizing something totally different because then you're not solving the original problem. Okay, so this alignment property is very nice to use. The trouble with using the difference evaluation function, though, is that you need to have access to the analytical representation of G. You need to know how to calculate this so that you can shove in some other numbers in there so that you can work out what this counterfactual is going to give you. So you don't always have access to this function G, but you know, you can approximate it, which is not so bad. But every time you approximate, obviously, you introduce places where you could have errors. So how would you approximate it? Well, let's say that the agents have access to the local state in action and the global team evaluation, which is what we assumed already. And now we can have every agent maintaining a private approximation for G. So here, really, they're just linearizing the global team evaluation around their own states and actions. So how much do I really need to know about the whole function G? I really just need to know about the bit around the actions that I'm taking. And so then we can just replace G in the previous slide with G hat, and we'll have a good time. So again, with this one, with the approximation, we're just looking at the difference between the system objective function and the approximated system objective function if agent I took that default action. Okay, so does it work? That's the real question. So we tried it with the rover domain, and yeah, it does all right. So G, if you just learned using the global reward, it's not very effective because there's all these issues of people being lazy, teammates being lazy and not actually, spreading out to see, collecting more useful information. D is kind of the best that you can do because you have all of your information about what everybody else is doing. And then our approximation lies somewhere in the middle over here. So it does all right. But when you consider what's actually happening, we have, what is this? A 12% decrease in performance between here. But these agents over here, this team here, has 90% less information about what's going on because they only know what they're doing. They don't need to know what everybody else is doing. So this is pretty good. For 90% less information, you will only have a drop of about 12% in terms of your team performance. Okay, we can scale this up even further. We can say, well, if we have a system where we now have 100 rovers, how well does this perform? Well, does this drop get any bigger? Actually, not too bad. I mean, now we're getting about 79% of what D is getting over here, so we have a drop of like 21%, but we're getting 99% less information than what this blue line is using to solve. So on the whole, not too bad. Okay. So of course, we're very excited, but we wanted to see whether or not the policies that we learned were actually any good. So we did the thing where we found some old robots, we dusted them off, we put on some very simple ROS nodes, and then we basically pumped in our learned control policies to see what would happen. And so here, what you're going to see is we have leg detectors running on every single one of these robots, and they're basically trying to find all the people in the system. They have to run around and kind of get close to all of us. Let me see if this will work. I have to say this is, given what I've seen of all the other presenters, this is a very rudimentary robotics experiment, but we were more excited about the theory that we had underlying it, and at the same time, the fact that we could see things moving around was also very exciting. So this is Khan over here. He was actually the most excited of everybody in the room. He was the professor of the lab at the time. And these robots have been sitting in a corner for, I think, 2 years of his office. And the fact that he saw them actually driving around again was the only thing that made him happy. So that was my work done for the whole year. Okay, so this is just showing that we had it running with ROS, so you could do the leg detection work. But what's cool is that basically you can reconfigure your whole space. So you can have dynamic environments, and even though the points of interest have now moved, because the control policies never needed to know that the points of interest would stay static, basically they could continue to run, they would again congregate around where all the people were, and except for some guys over here which just got stuck and broken, as I think you guys are all familiar with as well. Oh yes, and finally the last guy is going to come over and join us. Okay, so we've been talking a lot about reward shaping, but there's a very big caveat that comes with this. This is my big user beware slide. Reward shaping can be very, very tricky to get right. And the reason is that your reward is part of the Markov decision process definition. And it has a strong influence on defining exactly what the task is. So if you muck around with your reward function, your learning algorithm is not going to know anything about that. It's just going to try and maximize that reward. So you add additional terms on there, you divide by various factors. It's not going to know what your intention is. It's just going to try and maximize that reward function. And basically, I really like this quote, RL as a demon that's deliberately misinterpreting your reward and actively searching for the laziest possible local optimum. And I think for anybody in the room who's worked with reinforcement learning or learning in any kind of form, you will be very familiar with this. You'll have people who are like, oh, you know, I actually would like them to go a bit faster, so I'm going to add a term in here which is going to penalize them going slowly. And all of a sudden, your robots are spinning around in circles, and you don't know why. The reason why is that you've changed the task. Okay? So you have to be absolutely careful when you do this. And so the thing that you're looking for is to make sure that when you do change your reward function, or if you do add some bells and whistles onto it, that you still maintain some guarantees. So for example, you can have potential-based reward shaping, which is guaranteed to not change the Nash equilibria of the final solution of your coordination problem. Or for example, the difference reward function, which maintains the same gradient. So that partial derivative solution, which showed that if you maximize D, you're going to be maximizing G. And that's really important to have, because otherwise you could be solving something totally different and totally obtuse to what you actually wanted it to do. Okay, so this is the structural credit assignment problem, the lazy teammate problem, as you might want to remember it with. So let's move on to the next one, agent noise. And what is it, and how is it different to the structural credit assignment problem? So let's go back to this multi-rover exploration problem. And let's just simplify. Let's say there's only 2 agents now. So at learning epoch t minus n minus 1, let's say these are the actions. These are the trajectories that these 2 rovers took, and these are the kind of observations that they sent back. And our external evaluator is very happy with it, and it tells the 2 robots, and so they think, great, I've done a good job. So at learning epoch tn, now we're going to have possibly some different actions that are going to happen. So say our first robot, it doesn't really update too much because it was happy with what it was doing, so it nudges the trajectory a little bit, doesn't change its policy too much. But say our second robot instead tries to do an exploratory action. So now it's all the way out here, it's not really giving any useful information back to the system, and now our evaluator says, actually, you guys are doing a terrible job this time round. So this versus this, given that this agent has only made a very slight change to its policy, is going to look like random noise. It's going to look like mess. And it's going to make it very, very hard for this guy to figure out what exactly happened, especially if it has no information about what this guy did at all. So to unravel these kind of changes between learning epochs, you have this issue where you have to explore to find out where the good policies lie. But at the same time, when you explore, you're kind of stuffing up everybody else's answer, because everybody else thought you were going to do something, but then you kind of upended their expectations and you went off and did something else totally. And so then your reward signal gets turned into what looks to be like random noise. And so this is unique to multi-agent systems, obviously, because you need to have somebody else in the system who's stuffing up your answer. And so the existence of these independent concurrent learners changes the environment across our learning epochs. And so each agent's policy update is going to shift the goalposts for all of the other teammates who are trying to coordinate with it. And so your repeated actions, your repeated policies are going to have results that are that look like they're drawn from totally different distributions. And this is, again, one of those problems that we mentioned at the start. And so if you want to think about how the relationship between structural credit assignment and agent noise, you can think of structural credit assignment as intra-epoch noise. So within one epoch of learning, we're trying to work out the noise that's generated by other agents' contributions, whereas agent noise is inter-epoch noise. So across epochs, what is the noise that is generated by other agents' learning? And this is how these two are related. Okay, so how do we deal with it? Well, there's a couple of different ways that people have tried. The first one I list up here from Bowling and Veloso from 2001 is win or learn fast, and it's used mostly in adversarial settings. It's a very simple mechanism where basically if you're winning against your opponent, you keep doing what you're doing, but if you lose, then you bump up your learning parameter, like alpha, for example, in RL, and then you try and basically recover as quickly as possible. But we're looking at cooperative systems, so coordinated systems. And in here, we can either use clean rewards, so coordinated learning without exploratory action noise. We worked very hard for that acronym. And then we can also try probabilistic learning updates. So let's take a look at each one of these. So in clean rewards, basically what you're trying to do is remove all of the exploratory action noise in what is executed by the team. And basically put that all into some internal hypothesis, internal simulation. So instead of actually acting out all of your exploratory actions, you really just hypothesize what would have happened. So this is a very similar formulation to the difference evaluation function, but instead of saying what would have happened in the world without me and so on, you're saying, well, this is what the team actually did. What happens if I did something else? Same thing again, very similar. But you're not restricted to just comparing against what actually happened. You can compare any two scenarios, really. So what's recommended is actually that you compare against some counterfactual, some baseline performance of the team. And that's usually when you try and remove that particular agent from the system, you're actually trying to see how much improvement is it including to include that agent back into the system. And so because we're simulating all of this stuff, each agent is basically running these simulations on their own. You can do batch updates, so you can run as many of these as you like or as much as you have computation available to you or time. But of course, the drawbacks are that you need to have the functional representation of G in order for you to query these two things. Of course, you can always approximate. And it also makes every update step much more expensive because you're running a whole bunch of these calculations in the background, trying to figure out, what are all the possible things that I could have done, and how much better or worse are they. Okay, so does it work? Oh yeah, it does pretty well. This is a pretty busy slide. So again, the ones that I want to draw your attention to are the batch versions of the Clean Rewards 1 and Clean Rewards 2. These guys are the ones up here. It's probably not that surprising because they get a lot more access to simulating all the possible different variants that could have happened in the environment. But even just using the straight up Clean Rewards, you're still doing better than what G or D can do, which is down here. Okay, so that's one option. The other one is that instead of trying to pigeonhole the exploration internally, how about we actually just be very selective about which one of the agents we allow to update their policies. And so this is what probabilistic learning agents is trying to do. So instead of allowing everybody to update their policies at every learning epoch, we say, look, we're only going to let the agents that are actually doing something useful with their learning update that. And the way that we try and turn that into math is by saying, let's compute the impact that an agent is making. How much impact is their learning making? How much difference are they making? Given that they updated their policy, did the reward dramatically change? And so you can measure this impact in a bunch of different ways. Here's one example where we're looking at what is the difference in the reward given the change that you've made to your policy. So if you have made a very big change to your policy, you made a massive update, and nothing really much happened up here, it means that you probably don't need to learn anymore, right? So the bigger this number is, the bigger this impact number is, the more likely that agent is to learn. So if it's not making a huge impact, then you can probably stop learning. It means that you make the whole system a little bit more stationary and everybody else has an easier time trying to keep up. On the other hand, if you made a very small change here, but there was a really big update to the reward function, well then maybe you want to keep paying attention to what's happening. So how do we actually get these values? Well, if we're using Q-learning, the change in your policy is very simple. You can actually just calculate it out of the temporal difference. This is what delta pi is going to be. If you're using neuroevolution, it's a little bit trickier because you're trying to compare two different neural networks. And there's a lot of numbers that are going on in between here. And so one way that you can think about it is, well, each one of these connections are a set of weights, which form some sort of matrix operation getting from one layer of the nodes to the next. And so we can actually compare these two across all the layers by using something like the Frobenius norm or any other one of your favorite metrics for comparing matrices. Okay, again, the question, does it work? So we tried it out on some very simple domains, and yeah, it seems to not do too badly. Well, we'll see. This tau parameter that was there on a couple of slides ago, if I can bring it back, this one here, which I conveniently did not mention to you, is going to rear its head, and we'll discuss it a little bit more towards the end. But here, this one here, this blue line that is kind of dropping all the way down the bottom at the beginning, but kind of rising towards the end, this is when we allow everybody to learn all the time. And what you notice is that, it does all right in terms of learning, but it doesn't actually converge to the optimal solution until very, very late in the game. Whereas if we become selective about who we allow to do their updates, we can actually be a little bit faster in terms of our convergence. So look at this purple line, actually, it converges all the way at 1,000 time steps, whereas 1,000 epochs, whereas if we allow everybody to just be learning all the time, then it actually becomes like 3 times or more slower. Now this tau parameter also basically scales how many agents are learning at once. So if you have a very small tau parameter, basically you're allowing anybody who's making any kind of a difference to update their parameters. So you have a lot more agents learning at once up here, but as you make this tau parameter much bigger, then you end up with very few agents learning at once. Of course, it's not always the same agent, so it's a different set every time that you're running through this. But basically, you're just being more selective about saying, okay, now you're allowed to change your policy, whereas everybody else stay the same. Okay. But of course, there's a bunch of dirty laundry that's hidden underneath the hood. And first of all, this P-learn parameter is pretty arbitrary, right? I mean, you can pick whatever you like, really, to decide who's going to learn and who's not going to learn. And more to the point, that tau parameter that we threw in there, anytime you put in a parameter like that, people get really nervous because it's another thing that they're going to have to optimize or learn or figure out, and basically your whole system could be very sensitive to any kind of parameters you throw in there. So that's one thing that we never really addressed in this work, but we showed that if you're careful about it, it will work pretty well. And the final thing is that the guarantees that we provide here are generally not super strong. In terms of being able to show alignment or to show that it's going to still converge to the same Nash equilibria, we're still unable to make very strong statements about that. Okay, but these are a couple of ways that you can start to address this idea of agent noise. So how do you deal with the fact that every time you update your control policy, you're shifting the goalpost for everybody else who's trying to learn to coordinate with you? And that's happening, m times, where m is the total number of agents in the whole team. Okay, so agent noise. Let's move on to the last problem that I want to discuss with you, which is tightly coupled tasks. So here, I think Antonio Franchi's talk already introduced this idea of tightly coupled jobs or tightly coupled tasks. But let me just give you a quick recap on what we think of when we talk about multi-agent learning literature. So we're back here in the multi-robo domain. This is what everybody has observed. But say now, instead of having one observation of a particular point of interest, we need to have multiple. Say we need 3. And observations are kind of a silly example, but for example, it could be something like shared load carrying. So one robot might not be strong enough to carry the full load. You actually need 3 of them to be coordinating at the same time. So you need them to be simultaneously doing the same thing at the same time. Okay. So in that case, all of these other samples, all these other observations are going to receive no reward because we needed 3 at once. And so the only one that we get is going to be this guy. And so the reward that comes back from our evaluator says, you did all right. You did all right. But how are we going to propagate this information to this whole team? All the problems that we have with structural credit assignment, agent noise, they're all going to still exist. But now we have this additional constraint where not only do we need one agent to be doing something at the same time, we need them to be tightly coordinated. Okay, so when one robot just isn't enough, this is cases where we have strict constraints on the coordination. So to compare, we can have vacuum cleaning robots where you could just put your Roomba in one room, you can get another Roomba and put in another room, and they can work without ever really needing to have any tight coordination in terms of their timings or anything beyond just staying out of each other's way. Whereas on the other hand, if you have furniture moving robots, then you can't just have a robot come over and try and pick up the chair and then walk away. You need 4 of them, for example, if that's how many it takes to lift it. You need all 4 of them to be at the same place at the same time, coordinate their actions, and then they can succeed at the task. And anything short of that is going to not achieve the task. So I guess the problems are really apparent. Basically, you've now exponentially shrunk the space of informative rewards. A whole bunch of your search space, a whole bunch of your state action space just gives you 0. And this is a really huge problem for learning because learning requires a gradient. Now, if you just keep getting 0s the whole time, you're just going to continue to explore randomly until you get the first signal, which is non-zero or different at least, and then you can say, okay, this is different to everything else. I know which direction that I could potentially head to get some more information, to get possibly a better result. And so because of this loss of gradient information, it becomes very, very hard to solve these kinds of problems. And especially when we look at the kind of evaluations we get, so the global evaluation, we talked about it already. Not very useful. It just tells you how well the whole team performed at once. If we look at the difference reward, which we introduced earlier, well, let's do a case study. So if we have the difference reward, let's first look at this agent over here. Can you see this one that's kind of flashing on and off? So if this robot, this agent here, is now going to run the difference reward. So it says, okay, what is my counterfactual? Well, let's say I did nothing. I stayed at the start and I didn't move. I can calculate what the world would have been like had I not done what I did, because basically this observation, this sample wouldn't have succeeded because there would have only been 2 other robots here if I'd stayed where I was at the beginning. So I now know that if I had done something else, the system reward would have been lower than had I done exactly what I did this time around. So when it does this difference reward, it says, well, this is what I got, this is what could have happened if I performed my counterfactual action, and so I know that on the whole, I'm doing all right. I should keep doing what I'm doing. Okay, and all of these 3 robots are pretty much going to get the same kind of difference reward evaluation. Now on the other hand, let's now look at this guy in the middle here. So this agent over here, it kind of wandered off in the direction of where the samples were, where the interesting stuff is. But when it runs this difference evaluation, it's going to say, okay, what happens if I stayed where I was? Well, actually nothing would have changed. You know, had it been here, had it been over here, there's no difference. So when it does this calculation, it's basically saying what you did was rubbish, try something else. And in fact, all of these agents over here, all of these robots are going to get exactly the same signal if they try to use the difference evaluation. So this is not very useful. It's not very informative because all they're getting are zeros all the time, so they don't know, which direction should I head to actually try and get a better reward. Now, the really critical thing is that regardless of whether it's single agent learning, multi-agent learning, all learning is predicated on an agent stumbling on the right action. So you have to find something to begin with, find something useful. Otherwise, if it's all zeros, it's all uninformative, and all you're doing is exploring randomly. When we have tightly coupled tasks, we now introduce this additional constraint when you need multiple agents to stumble on the right action at the same time, or at the right time, shall we say. And so all those issues of having no gradients, of having these step changes, means that it's going to make it a lot harder to stumble on that right action. So what we need is that we actually need a mechanism that's going to allow us to reward some of these stepping stones towards successful coordination. And by stepping stones, I mean, like, if you need 3 robots to coordinate to do something, then perhaps if one robot is kind of doing the right thing, then instead of giving it 0, you should give it something greater than 0. And then if 2 of them are doing the right thing, you should, again, give it a bit more. And if all 3 of them are doing the right thing, then hooray, you've achieved your task and it has the highest reward. But basically, we're trying to reintroduce this gradient back into a system which basically has points in this very high dimensional space. And so when we reintroduce these gradients, hopefully it makes the learning a little bit easier. Okay. So what does it look like mathematically? Well, if we consider perhaps what a super agent could achieve. So each individual agent, this is kind of coming back again from the clean rewards formulation, so hypothesizing what the world would have been like had something else happened. We can say, well, if I had some other counterfactual agents helping me out. So if I was trying to lift up this table and I needed 4 other agents to lift up the table with me, say I can lift up a corner, I can imagine, well, if I had 3 other people here with me, then we would actually be able to achieve this task. And so I haven't actually achieved it yet, though, which is why I have to scale according to how much more I need help with. But in that case, we can still get some kind of information from the system to tell us, you're doing all right. Keep trying. Maybe somebody's going to come over and help you later. So this first term is the global system performance, where we have multiple copies of people doing the same thing together. Again, we have the global system performance. And this reward function here, D++, provides all of our agents with a much stronger feedback signal, which is not just zeros everywhere in the space. And this allows us to really target these stepping stones that lead to achieving the system reward. All right, so if we go back here. So back here we had the difference reward, which was giving us all of these agents exactly the same reward of 0. But these ones over here, they were getting something useful that they could learn with. Okay, so if we try with D++ now, if we take a look at this agent in the middle again, if it's going to hypothesize that it has one other agent with it, well, that doesn't change anything because they're still not able to receive any rewards. They need 3 to be there with them. So still, when we do our little thumbs up, thumbs down algorithm, it's still going to get a 0 from there. Okay, now if we have two, if it hypothesizes two more agents with it, well now in this case, the observation that it takes is actually going to count towards its global team evaluation. And in that case, it's going to change what the evaluator provides. So then we can do our calculation. We can say, all right, if I had two other agents with me, then I would have successfully improved my team reward. How much would I have improved it by? Well, some amount, and then I have to scale it by how much I had to imagine, how many other people had to be helping me with that. Okay. And so actually these two agents over here who are actually doing something that's getting towards being a useful skill inside this whole team are going to receive that kind of reward, whereas these guys over here who are really, there's no chance. No matter how many more agents come and help them out, they're still going to be not contributing at all to the system. So these guys over here will still get a reward of 0 because they still need to find that first step towards successful coordination. All right, so does it work? Well, let's see. So for 3 simultaneous observations in this environment, these are the kinds of results that you're going to see by using G or D. The D is a little bit better. The difference of reward is still removing some of that structural credit assignment, but still not performing that well. If you use D++, then you get this very large boost. Of course, you are using a lot more information because you have to hypothesize what could have happened. So what do these control policies look like when you actually go and put them out into the world? So say these are our robots here, and these here are our points of interest. The bigger the circle, the more information there is to gather from there. And so if we have a look at the kinds of policies that we get, we see that, they've kind of split into teams to go and collect this information. So, the policies that they're learning are actually quite sensible. Of course, you still have some agents that have not learned what to do or how to coordinate with people. And if you notice here, there's actually 4 agents going across here and 4 over here. So it's not the most efficient way, but it's certainly doing better than G or D can do. Okay, so let's make it harder. This was only 3 simultaneous observations. What if we need 6? Well, if we need 6, then it becomes almost hopeless to try and learn using G or D. They're just not going to have any reward signal because you need 6 things happening simultaneously at the same time. Everybody has no idea what it was, but they have to stumble on this right action at the right time together. It's almost not going to happen. Almost surely not going to happen. This is what that shows. Of course, if you provide information about these stepping stone rewards, then yeah, actually it goes from being impossible to being hard, but still possible. There's that. All right, so the dirty laundry. Again, we still need a functional form of G, so if we want to go around mucking around with hypothesizing what the world is going to be like, we need to be able to access the functional form of G or some approximation of it. And on all of these examples, we've only tested it for additive tasks. One where basically everybody does the same thing, and we just need more and more of them in order to finally achieve that task. And so what happens if they're not additive tasks? What if they're temporally coupled? What if one agent needs to, lift up the table here and another one needs to turn on the light over there at the same time? And that suddenly makes all of your joint combinations of actions grow very, very large very quickly. So it's going to scale very poorly when we're starting to think of kind of other scenarios where we're not just looking at additive tasks. So, but it's a first step. We'll start to see how else people can try and address these problems. Okay, so that was tightly coupled tasks, and these are kind of the 3 big problems in multi-agent learning: structural credit assignment, agent noise, and what happens when we need agents to be doing exactly the right thing at the right time with each other. Okay, now I want to take a step back, and we're going to get a little bit philosophical. This is the part where I say, we haven't had any drones. We might not even have any robots at this point, so we'll see. So the question that we want to answer here is, we've been doing a lot of multi-agent learning, and for most of these problems, it's been pretty clear what the agent is. If I showed you this picture and I asked you, what's an agent? I think a lot of people will say, well, that's an agent, one robot. This is a robot, it's a whole contained system, but perhaps we could think of another breakdown. What if I wanted to say, what if all of the defense robots were one agent and all of the offense robots were controlled by one agent? That's also possible. Agents are not, strictly required to be, one robot. It's a pretty flexible representation that we can have. And if we wanted to take this all the way to the other end, we could have a centralized agent that controls the whole team and basically revert to a single agent problem at that point where we are learning the joint state action for all of the team at the same time. If we looked at the tightly coupled multi-rover exploration domain where we needed 3 agents to simultaneously observe one of these points of interest at once, well, actually, we could have made our job a lot easier if we just said, like, instead of each one of these robots being an agent, why don't we just make a group of 3 robots be controlled by one agent? And then we can basically remove a bunch of these problems of, having to guess at what everybody else is doing. We can just have one agent that can see and control all of the things that this set of 3 robots are actually doing. Okay, so that's with the kinds of problems that we regularly think about in terms of multi-robot systems. But multi-agent systems are even more flexible than that because we can deal with problems like this. So say, for example, you're working for the City of Prague's transportation system, and your job is to try and improve the throughput of all the people who want to use the roads, the metro, the trams. And so you get to decide, for example, how long each traffic light is going to be on for, how the traffic lights are going to coordinate with each other. And in that case, we can think of this whole thing as a multi-agent system as well, where each of the traffic lights could be an agent. But at the same time, it doesn't have to be a single traffic light. It could also be, a block of traffic lights or a street of traffic lights could be controlled by one agent. And like the imperative thing about these kinds of domains is that each of the individual actors in the system, like the drivers of on these roads, you don't get to control their actions, right? I don't get to tell all of the drivers, which way to turn. I mean, Google Maps will tell you which way to turn, but Google Maps is basing that off how long they predict it's going to take or how much it's going to cost these drivers to get across this system. And so if we can manipulate that by changing how long the lights take to change and so on, we can actually start to make a difference about how congested this whole system is. Okay? So it's kind of a little bit disturbing to think about AI controlling our actions. So instead, we like to use this scenario instead where, the robots are back, don't worry. So there are no robots in this scenario, but there are robots here. So we can have something like the Amazon warehouses, where they have a lot of these Kiva robots that are driving around, basically taking shelves from one place to another, delivering things from one place to another. Now, each one of these Kiva robots is running a very simple path planning algorithm. And there's probably some coordination that's happening at the operational level, which is saying, don't take this particular aisle because it's too busy, so take another aisle and so on. But basically, we can formulate it in the same way instead by having a multi-agent system controlling, how much does it cost to go down any one of these paths. And so actually, this kind of an environment is very nice and very conducive to asking the question of what is an agent. So if we take a little bit more of a closer look at how we formulate this, well, each one of these begins with a graph of some sort. We have some cost associated with each one of these edges, and some capacity associated with the edges. So, there might be robots are able to drive along here, 3 autonomous ground vehicles, but only 2 up the top and so on. Okay, so we can populate these with our robots, but I want you to kind of bear with me. And in this case, keep in mind that the robots are not the agents. This is something that we are really emphasizing to our reviewers, because many people will read this and they'll instantly think, oh yeah, the robots are the agents. No, I want you to think that the robots in this case are not the agents. They're the physics of the system. They're the things that are driving us and deciding, how well does the system perform in terms of congestion. The agents will come later. Okay, so we can have capacity represented by the current number of robots on each of these edges. And actually in these systems, we can also represent 2 different types of loitering. So in this case here, we can have robots that have, finished their delivery, so they've gotten to their destination, they dropped off their stuff, and basically they exit the graph at that point, and they don't take up any more space on this graph. So that's why this one is white, and this one up here as well. But on the other hand, we can have robots which are still on their way to their final destination, but they're stuck, because over here, the edge that it's trying to connect onto is actually full. So it has to wait here. And so because it's waiting here, it's still taking up space on this edge. And so as you can see, if you're not careful about basically how you route all of this traffic, you can end up with a lot of congestion. Okay, so what can you do as a multi-agent researcher? Well, you can say, instead of just having any odd cost associated with this, we can actually, manipulate this cost. So we can have some fixed cost of travel, how long it takes to get across there, but then we can also put additional terms onto that. and say, we can artificially inflate how expensive it is to cross this path or this path so that we encourage the robots to take a different route to get to their goal. And so this is how our multi-agent system is going to come about. So given this kind of a problem, we have, I think, a number of different ways that you can represent an agent in this system. So the first and most simple one is that you can have a centralized agent. You have one guy that is controlling all of the costs across the entire graph at once, and he can see everything. He can see how much traffic is everywhere. Of course, this is a very big problem. On the other end, we can have a very small learning problem where we have one agent controlling a single edge. A link agent, let's call it. And that link agent can only see what's happening on this particular edge. It can only control how much additional cost is going to apply to that particular edge. And somewhere in the middle, we can have intersection agents where we look at all of the incoming traffic to a particular intersection. And then that agent can basically control all of the costs that are associated with those edges that are connected to that particular vertex. And so what we can immediately see is that given these different agent definitions, so we have centralized agents, intersection agents, link agents, what's different about each of these ones is basically, one, how many of these agents are going to make up your team. So in the centralized agent team, there's only one agent, so it's a single agent system. But in the intersection agent team, well, typically you're going to have fewer of them than link agents, but more of them than centralized agents. And so what makes it tricky is that over on this side, over on the link agent side, you have agents which are not super powerful. They can't see a whole lot in terms of the global view of the system, but they have a very simple learning problem to solve individually. Coordination is hard, but individual learning is easy. And on the other side, centralized agents, the learning is hard because now you have this very large dimensional problem. So you're trying to do reinforcement learning over a very n to the power of however many edges and links that you have in here. And so although your coordination is effectively perfect because there's only one agent, so you coordinate perfectly with yourself, the learning itself is quite difficult. Okay, so we want to have a look at this in a little bit more detail so that we can really understand basically what kind of scales we're talking about. So we have link agents. Well, if this link agent can only see what's happening on its edge, then the only information it has available to it is really how many AGVs are currently traveling across my edge. We can give it some additional information, which is, for example, how long it's going to take the next robot to get off, because that could be useful as well. And we also know that there's some capacity constraints that are associated with it. So that's what a link agent looks like. We can have an intersection agent, which is going to be quite similar, but in that case, we're going to have a larger dimensional problem, so it's going to be the number of incoming edges, and there's going to be some count across all of those. And then, as well, you can add the time information. And then for the centralized agent, this is the biggest one. It's going to include all of the information, where all the robots are at all times, how long it's going to take each one of these robots to get off the edge, i.e. how the system is going to change over time. And all this information is going to be available to that agent. Yeah, one thing, these guys over here, they won't be considered. Because they're outside of it, they don't take up capacity, but this is a technicality. Okay, so when we look at this set of options, then this is just a small set of options that you could have. You have your link agents. The number of them that you're going to have is going to be the number of edges that you have in your graph. Intersection agent is going to be the number of vertices that you have in your graph, and the centralized agent, well, there's only one of them. Now, the state and the state dimensionality for each one of these is going to go from only one, because it's just going to be a count, all the way up to the full system, plus the information about timing and so on. And similarly for action. And the one thing to take away from all of these kind of squiggles on the screen here is that the more you go in this direction, the more agents you're going to have in your system. But what you're trading off is the complexity of the individual learning that you have here. So even though your coordination gets harder, so the more agents you have, the harder the coordination is, the individual learning gets easier because the state and action dimensionality stays relatively small. So there's no free lunch, right? So at some point, somebody's going to have to pull some weight and learn actually what the optimal policies are. You're just trading off where that complexity happens, whether it's in the coordination or whether it's in the individual learning. Okay, so very quickly, this is just the graph that we ended up testing on. It's a very simple kind of graph where everybody's trying to get from 0 to 1 or 1 to 0. So they're split in half and they're all trying to go across. This is like a highway, if you want to think of it that way, and these are the small streets. And just to highlight, we're going to do some robustness studies later on for vertex 2 and vertex 6, and each of these incoming edges are the ones that we're going to be talking about. Okay, so let's just have a look at kind of the complexity of the system in terms of the solutions that they learn at the end. This video is going to play, and then there's going to be a whole bunch of circles moving around, so I'm going to try and explain to you what it is that you're looking at. So up the top, you're going to see the kind of agent team that we're using and the number of robots that are in the system. Actually, what I didn't mention before is that given the full capacity of the system, we can only, if this is a parking lot, if we shoved as many robots as we could into here, we could only fit 272 robots in here. So we test all the way up to 400 just to see what would happen. Like, how hard is it really? So this will tell you how many robots in there, and this number will keep count of how many successful deliveries, how many robots were able to make it to the destination, drop it off, and then they continue. So once they get to the other side, they come back. So in here, all these little dots are our AGVs. They're moving across these edges, and the cost of the edges are listed here. So some of the edges are going to be lighter in color, and some of them are going to be solid in color, and the amount of solidness, if you like, is how full that particular edge is. So these guys up here, they're totally full. This one down here is only half full. And then if we do have some robots with gray around them, it means they're waiting to enter the graph. And some of them you'll see will have red around them. That means they're still en route, but they're stuck. They're stuck trying to get across to another edge. Okay, so let's see if this will play. So just to give you an idea, this is at the start of learning. We use neuroevolution in this case, and it's very unexciting. The very first thing it tries is just to go across the shortest path. Not very successful, right? So there's only like 200 and something successful deliveries. If we use neuroevolution and we try and work out, what are some better strategies for doing that, then we start to see it spreading out. We start to see our agents spreading out this traffic across the space and being able to use more of it. So that was with link agents. This is link agents with the timing information. You can see that they use more of the space. But let's see what happens when we have a really difficult system. So this is 400 robots all trying to move across this graph, which can only fit 272. And what you notice is that there's a lot of congestion happening in here. There's a lot of red. And obviously there's going to be a lot of gray because a lot of people can't even get into the system to begin with. So that was with the centralized agent. This is with intersection agents. And actually now you see there's quite a bit less congestion going on. They're using all of this space out here as well, whereas before the centralized agent had kind of not figured out that it could use all of the different edges that were connecting out to the outside. I think this one may be the most successful one if we have link agents with time information. We go from something, I think originally it was 500 and something successful deliveries, and this one gets up to over, I think, 800. Oh, close to 900. 900 successful deliveries. So it's possible. For something that starts off really stupid, not knowing anything about the environment, it's able to basically explore, discover these strategies, and learn to coordinate. Okay, so just taking a look at what happens when you increase the number of robots in the system. This is basically making the task harder. We see that, at the start when there's not that much congestion, it doesn't really make a big difference whether you use a link agent or a centralized agent. None of that really matters because you're not stressing the system that much. But once you get up to these harder problems, when you have a lot more congestion that's possible in the system, it actually does make a pretty big difference. Like these centralized agents, this light blue line down here and also this green line down here, simply don't perform quite as well. The other thing you'll notice is that these two, the centralized ones, are monotonic, which is what you would expect, right? If you're learning in a single agent system, you shouldn't forget, or at least hopefully your algorithm does not forget good solutions. But when you have multi-agent learning, you have all these problems of the non-stationarity, of the structural credit assignment. And so occasionally, you'll find a good solution, but then you'll lose it again because one of the agents in the team has decided to explore somewhere and then everybody else is panicked and can't figure out what happened. Okay, so this is showing you the best performance across each of the learning epochs. If we just look at the very end, we can look at the final team performance distributions. And I really like these plots. I hope the one thing that you guys take away from this is that everybody should be using either box plots or violin plots. And the reason is because you cannot hide behind the mean. So even if your solution does super well in the mean, I want to see what the distribution of all of your answers looks like across all of your random seeds. I want to know if there's like a really tragic thing that happens sometimes. So even though the mean looks fine, it's very interesting to always look at what the full distribution of your solutions looks like. And in this particular case, it's actually very informative because each one of these blobs, each one of these bumps is actually showing you a local optimum. So basically what this allows you to see is how well each one of these agent definitions is able to bump out of those local optima and basically push their solution upwards towards finding those optimal solutions up the top. And so as we would expect, the centralized solutions don't have as much of a spread. They're very normally distributed. But for these other ones here where we have an actual multi-agent learning system, there's a very big chance that you just get stuck in somewhere really crappy. But at the same time, they're also the ones that find those good solutions that are really just unattainable by centralized systems. And I think the final thing that I want to show you in this whole set is what happens when you have agent failure. So one of the big questions that comes up is how robust is the system to cases where an agent just really shuts down and doesn't do anything well. So in this case, we look at failure at vertex number 6. So this is the one in the middle. So what happens if link number 15, which I think is the one coming down from 3, starts just outputting the maximum, so basically blocking all the traffic going in that direction? Well, there's this big drop here that happens at time step 200 when when this failure happens, but they're actually able to recover quite well in these cases. And what's interesting is that we try to make it a fair comparison between the link agent definition and the intersection agent definition by looking at all this full set of link agents that would have contributed to the same intersection. And you see that actually having a more global knowledge of the system still does comparatively well between the two, so there's not too much in it. When we shut down intersection 2, actually the performance is much worse because this is one of the key intersections. You want to start pushing traffic through that direction just to get people off the main highway. And so if you shut this one down, then you have a much bigger drop in the performance to begin with. But then again, you're still able to recover later on. And again, looking at these final distributions, these first ones here are kind of like we only have one of the link agents failing, and so they're actually pretty good. If there's only one link agent that fails, obviously the whole system doesn't depend as heavily on it as if one whole intersection agent fails. But you can see that these are reasonably comparable in terms of their mean, but their distributions are kind of different, especially in this case where a majority of the blob for vertex 6 failure is, when you have the link agent team is much closer to a lower local optima compared to what the intersection agents are able to find. Okay, so this one I'm putting dirty in question marks because here we're not really telling you what the right solution is. We're just saying maybe people should think about how they choose their agent definition because clearly it makes a difference. And it can have quite a substantial difference in terms of the learn team performance at the end of the day. And so what you're doing is you're trading off between the locality of the learned agent policies and the complexity of learning this whole coordination. Remember, there's no free lunch. You're balancing between these two factors. And yeah, of course, there are many, many variations still to investigate. And these are all big open problems that hopefully some of you can help us out with because I'm getting kind of exhausted looking at these little squiggly lines all the time. And I think we need some fresh ideas to try and reinvigorate this area. Okay, so that pretty much brings me to the end of the talk. Some kind of take-home messages, I suppose, are, first of all, that multi-agent learning has been demonstrated to discover really complex coordination strategies. So in those traffic routing problems, I don't think I could do that. When there's 400 of those dots moving around, I don't think I could come up with an optimal strategy for how to route all of this traffic. I think learning them is quite a viable solution. The problem is it can also exacerbate existing challenges in single agent learning. So the 3 problems that we talked about, structural credit assignment, agent noise, tightly coupled systems, all of these things exacerbate existing problems in learning. The need to explore exhaustively, the need for stationarity in your reward function, and the need for observability across your whole space. All these things, all the guarantees that are associated with them basically get thrown out the window when you start looking at multi-agent systems. Problem representation is, I think, possibly the most important part of multi-agent learning. How you decide what your agent's state, what its actions, what the rewards for the whole team are going to be. They really define how easy the problem is to solve and whether or not you're even solving the right problem to begin with. And finally, again, user beware. Reward shaping is very tempting. It is something that I see a lot of people doing and not doing very effectively. And so one of the things that I hope you really appreciate after listening to this hour-and-a-half ramble about multi-agent learning for coordination is that reward shaping can be powerful, but it's also really, really tricky. You need to respect the rules of how you define your problem. Don't just go mucking around throwing variables onto the end of your reward function because you wanted your robots to go a bit faster. Okay? You got to really think about it. Okay, so with that bombshell, this is my wall of faces. These are all the people that contributed to the work that I talked about to you today. Again, like I said, a lot of this work was done while I was at Oregon State, working with Khan Toomer, Jeff Hollinger. I'm now at ETH Zurich, working with Roland Siegwart, and we also have a lot of collaborators from across the world. Okay, I noticed a lot of other of the talks were giving you like a nice reading list, so I thought I'd compile my own. If you're interested in multi-agent learning for coordination, I think this is a nice set of papers to read that really talk about it from the start of learning. Of course, there's plenty of new papers that are coming out all the time, but I think these ones really set the baseline for what the challenges are, how the problems are defined, and really what's hard and what's interesting for people to research. And of course, read the textbook. It's a really good one. Okay, I think that's it. Thank you very much.
Thank you very much for the talk. I see questions immediately.
Hi, thanks for the talk. It was very interesting. I have two questions about tightly coupled agents. So the reward is basically outcome of their behavior, right? So what if instead of like optimizing and improving the reward function, we put some more constraints on their behavior and motion instead? So for example, you've shown that in your, on one of your graphs, that one agent, it simply stuck. And so if we put some constraint on behavior, he would probably just start moving more alike to other agents, and so he will probably learn something. And that's the first part. And second part also, could we also understand that agents shouldn't communicate, right? Because you focus on concurrent.
Not that they shouldn't, but they don't have to.
Okay, yeah. But can we embed somehow to the reward function that they can see the rewards of other agents, so they kind of compete with themselves? So that's basically the two things, the behavior constraints and embedding rewards. Thank you.
Okay, so the first question about constraining the actions that your agents can take. So yes, it's a possibility. Remember, again, the original paradigm of doing multi-agent learning for coordination is to really try and put all of your engineering effort into the learning strategy, and then letting the coordinations, the policies basically fall out from the learning strategy. So if you wanted to engineer the sets of actions that your agents can take, then you're kind of shifting your effort in that direction. It's totally possible and you can definitely do it, but then you have to be, again, careful about the representation. So is this constraint that you apply on the action that the robot can take dependent on what's happening everywhere else in the world? Or is it something that's always there? So you always need to be next to somebody. And in that case, you know, you're changing the definition of the underlying Markov decision process, right? Because the set of actions changes. And yeah, there's definitely ways. I mean, the three simultaneous observations is kind of a made-up problem, and there's a lot of ways that you can solve it without needing to go through all of this angst. But it's a nice one for us to demonstrate. So if you were practically going to say, look, I need 3 simultaneous observations, you would really just design your system so that you would never not have 3, right? But yeah, when we look at basically other scenarios where, you know, if you have furniture moving robots, where, you know, some things may require only 2 robots to do, others may require 4 or 10 or more, then you have to start being really careful about how you engineer this action space. Because if it's simple, I say do it, because it'll make your life easier. But if it becomes any harder than when you have to like really sit down and think about, okay, what was the answer going to look like? When you start asking that question, I think you run into the danger of basically engineering the solution before you actually engineer the learning. And the second question, which is about observing the rewards of other agents. So in this and in this whole talk, we assume that there's only one reward for the whole team. And it's possible that you can have individual rewards for everybody. So if they all had, this was like the local reward. So if you had some concept of, oh, I need to take observations of points of interest, then I can individually assess how well I did. And maybe I could broadcast that information to everybody else. But then, the question is, do I want to do that? Because then I have to communicate, and I have to make sure that I can receive it, calculate something useful out of it. And yeah, I think there's a possibility that could be useful in some cases. We don't consider those particular problems, but just using the local reward on its own without doing any additional manipulation we showed was not very good. So if you do receive the local rewards of everybody else, then yeah, you could probably calculate some version of the difference reward using that information as well. So I think it could be very useful.
Hi, thanks for your talk. I would like to know, when you do the robotic learning, do you do that with real robots, and then like you take the robot, you implement the policy for the robot, and you learn with the real system, or do you like do the learning and simulation and then transfer it to the real robot? How do you deal with that?
Yeah, that's a really great question. So we do all of our learning and simulation because it's easier. I mean, it's obviously not easy. It's definitely easier than doing it in hardware. So I think from the agents community, there's less of a focus. I think there was some discussion about ARMAS as a conference where they're more interested in the theory and less appreciative of the difficulties of using hardware. We're very aware of the difficulties of using hardware, which is why we like to do everything in simulation, and then transfer that to hardware systems. Part of the other thing you have to be careful of is this idea of transfer. So there's transfer learning, which is explicitly looking at if I trained in one system, whether that's a simulation of the real thing or not, how do I make sure that the things that I learned there are actually going to replicate on this new system that I transfer it to? So the way that we were careful about it from our perspective is we tried to pare back as much as possible what the representation of the states and actions and so on were going to be for each agent, so that we knew that when we put it on the robot, that robot was going to have the access to the same information, and that information would be robust to any of the kind of noises that you get when you're actually running it on real hardware. That said, there's definitely the possibility that you come up with a really beautiful, high-fidelity simulation, you learn fantastic control policies, everything's working beautifully, your lines are going all the way up to max really quickly, and then you put it on hardware and all of a sudden it just doesn't work. It's a very common story for a lot of people. And often it's because there's some disconnect between your representation that you learned on and the one that you're applying it to. There's something that you didn't model. There's something that you didn't model that was critical to the learning performance. And those are the things that you have to be really careful of. So yeah, if you're interested in this, transfer learning is the area, and there's a lot of people that are working on it, that's looking at how you train in one domain and then transfer it to a new one. And they can be drastically different too. They don't just have to be from simulation to hardware. But there's definitely theory out there which looks at basically trying to bridge that gap.
Hi, thanks for your presentation. So if we get more agents in our environment, that's likely, at least in some cases, to have like a different effect on the sort of thing that's got to be learnt as a whole, and it might affect what different agents can do, etc. So if we were to be in a case where, say, we had 5 agents or robots and they learnt an optimal policy through learning, and then out of somewhere we gained a new robot, or multiple robots, would it be possible to somehow take advantage of the previous policy we had learnt to then incorporate the new agent in, rather than just learning for this increased number of agents from scratch?
Yeah, and this is actually very closely related to the previous question. So there's transfer learning which looks at that, really, which is say, I learned when I was coordinating with 4 other agents, how do I now coordinate with 10? Like, the system has changed, but the task hasn't changed. And yes, there's definitely ways that you can do it. It also depends on the task. So like we were saying, with these loosely coupled tasks where you're just doing information gathering, you don't really have to simultaneously do stuff, in those cases, they're a lot easier to basically transfer directly. In fact, for a lot of them, you could like swap the policies around different agents and you would still get a very similar behavior. But for these tightly coupled ones, it's a little bit harder to say. So if you wanted robots that knew how to, do shared load transportation together, it's actually very hard to even say that if you had two robots that were holding a pole, one's on the left, one's on the right, that this robot's policy looks anything like this robot's policy. It's really hard to say because you have to look at what the state representation is, what the action representation is, because if it's looking at, for example, quadrants in space and where things are relative to it, it's going to look quite different to this agent's policy. But if you do it right, it could just be next to a pole where there's no other robot and the other one has exactly the same policy and they can basically do the same thing. So yeah, I think, again, representation is key. What is the problem that you're trying to solve? Is it additive? Is it loosely coupled? Is it tightly coupled? These things are all going to factor into how easy it is to transfer when you basically try and put more agents in or take agents out of your system.
Thank you.
Yeah, thank you so much for your talk. I was just curious, are there instances where a robot is doing nothing but there's no possible action for it to improve the overall reward of the system? And if so, how would you handle that, I guess?
I guess if you have too many robots and you really didn't need that many to begin with, so the kinds of problems where that would be the case would be like you've got saturation in your system. Basically, you're over-controlling for everything. Yeah, I think it's possible. Usually we have the opposite problem. Usually we have systems where we don't have enough agents. Actually, there's a full set of taxonomy which looks at how many agents do I have, how many tasks do I have, and if there's more of this one versus this one, how does it change the problem versus the other way around. I don't know. I haven't worked in any cases where we have this problem of this agent's really just stuck in a place where there's absolutely nothing that it can do to improve the system. But it's possible. And it's possible because in the joint state action space where the true optimal policy lies, there can be null spaces. There can be places where basically you don't need another agent. And these end up being cliffs that are very hard to kind of come out of. But we don't encounter them too often, I hope.
Thank you for your presentation. I just have a question about how to calculate a G for each agent. There are sometimes G is not just a simple summation of each agent. So it can be something complex, and so is it given by some exact formula, or is it given by determined by maybe neural network, or I wonder how to evaluate this reward for each agent.
Yeah, so G for the whole team is defined by the problem. So your problem, if it's robot soccer, it's the goal difference. If it's information gathering, it's how many bits of information you collected altogether. If it's furniture moving, it's how many pieces of furniture you moved. So this has to be defined by the problem itself. If it was additive, like you suggested, if it's just additive, then this is like ideal. This is very easy to learn because basically you do something, it's additive to everybody else's. So there's really no kind of tight coupling or anything associated with it. And it's fantastic. It's one of the easiest scenarios to imagine. But usually the assumption is that the environment will emit that reward to you in some way. So either there is some external accessor which is saying the goal difference is 3, and so you take that number 3 and then you do some calculation with it. And you don't really need to have access to the function of how G is calculated. Of course, for all of these fancy kind of difference reward, clean rewards, D++, all these things require the individual agents to have access to that G function. And so for the ones where we approximate using a neural network, or you could have any other of your favorite function approximators. So a linear function approximator, anything you like. And again, it will be a question of designing what it is that you think is going to be important, how much representational capacity you need to have for G, because we're linearizing about the individual agent's state action for D in any case, then when we use the single hidden layer neural network, that was enough for us to get an informative representation to approximate G by. But feasibly, you could use anything you like in that case.
Well, last question. If there is no, thank you again for coming and for accepting my invitation.
Thank you very
and
much.
I have also a small present for you. So thank you very much.
Thank you, Man. Thank you for your organization. It's been really fantastic, right?
Yes, before I will let you split into two groups again, I have to say something about the evening's program, because there are already some questions on Slack. So we will meet here at 6:30, 18:30, 6:30, outside, probably out of just before this building. And as we have asked you before, for your preference, we will be split into 2 or 3 groups. One group will be led by professional guide and give you to see some highlights in Prague. So going to Old Town Square, following the Charles Bridge, probably Castle. I don't know detail about these tours. And the second part of you can go with us for, we call it beer tour. So the plan is to just visit some interesting pubs in Prague. It's not organized. Like we will let it go like freely. So there will be some students. Probably I will also take part of one of the groups, and we will go to our preferred. I will repeat this information later. Or do you have it already? So if you can display it as well, because it may happen that some of you will not go to the briefing, for example, because of you are not going to the Friday's experiment. There are some of you, but you want to join us for today's evening. So let me tell it right now. So there are some instructions. So as I said, in front of building E, which is this building, we'll meet all of us at 6:30 p.m. Okay, so the route, two route we have already. So yes, I was correct. So Charles Square, which is here, Dancing House, which is a house on the bank of the river, then continue to National Theatre, then the Charles Bridge, as I said, Malostranské náměstí, Malostranské Square, okay, which is close to the Prague Castle, and then there is nice view from the Prague Castle, and then going back by metro or tram. Okay, the time of this tour is 3 hours, so hopefully you have still enough energy. Of course, you can leave the group whenever you want. The second, this pubs tour, okay. As I said, it will be probably 2 groups. So far, we have 15 people for each of you. If you want to change your preference, still, there is an option, but of course, there is a limited number of people that can follow the guided tour, the professional one, and also this pubs tour is limited because of limited people in my group, and we cannot come into these pubs. We cannot make reservation because we don't know times and we don't know how many people will go there, so we will just try to find pub which is free, and usually taking 1 beer is possible even if it's crowded. Yes, so yes, we have budget to cover beer in the first pub, but then we will each of us will pay the beer for ourselves. So that's it, most probably. Yes. Did I forget something? Yeah, the tomorrow program will be specified. We have the special slot after the presentation and the practicals. So if you can put back the slide, just what you know already, who should go where, right? So again, this how is it? Group A goes to East 132, B, C to E 230, and the rest D, E, F, G, I. No, I was already before, so just H, G, H will stay here for another presentation, the same presentation of Alejandro. So it has no sense to attend it twice. So for those of you who are not going to the practicals. And after that, we will have coffee break. The coffee break is late now purposely because we want to give you some some sweet to survive then these 3 hours of walking. There will be no dinner in this walking tour. Of course, if you will attend the beer tour, we can take something in pub. Okay, so hopefully it's enough, and please go to the to the rooms.